Welcome to the Deep Dive. Today we're zeroing in on Manzano, this new unified multimodal model from Apple. And this is pretty significant because it really tries to tackle a fundamental tension we see in these multimodal large language models.
Yeah, the challenge has always been this kind of performance trade-off, right?
Hmm.
You get a model that's brilliant at visual understanding, maybe reading a complex chart, answering questions about it. But then it often struggles with visual generation, like creating really high-quality images from text prompts. Usually they're good at one or the other. It forces a tough compromise.
And Manzano is claiming essentially that they've found a way to substantially reduce that tension. Their approach mixes two key things: a novel hybrid image tokenizer and then a very carefully structured training recipe. So what we need to do is dig into how they actually engineered this unification and, crucially, look at the performance data. Does it really solve that trade-off? Okay, let's start at the beginning then. Why is it so hard to get both understanding image to text, or I2T, and generation text to image T2I working well together in one model? You'd think they might be complementary skills.
Well, the conflict boils down to how the visual data is represented. Think about it like this. For autoregressive generation, the model needs to predict the next visual piece, the next token, sequentially, almost like building an image from blocks. So that requires discrete, sort of quantized image tokens. But then for deep understanding tasks, reading tiny text on a scanned page or analyzing a detailed graph, the model needs a much richer, continuous stream of information. It's more like reading a high-res file. A lot of existing models try to handle this with two separate encoders. One gets the rich, continuous features, and another handles the discrete tokens. The problem is the main language model, the LLM brain, then has to process two totally different types of data, these heterogeneous tokens, at the same time. And that cognitive load, well, it significantly hurts its performance, especially on the understanding side.
All right, that sounds like a real technical challenge. You're asking the LLM to juggle two different visual languages. So this brings us to Manzano's main idea, this hybrid image tokenizer. How does that design streamline things?
They simplify the input side quite a bit. Instead of two separate visual systems, Manzano uses just a single shared vision encoder. Think of it as the model's one eye.
Okay, one eye.
Right, and the single encoder feeds its information into two extremely lightweight adapters simultaneously. One adapter creates the continuous embeddings needed for that I2T understanding, and the other adapter creates the discrete tokens needed for T2I generation. And the real elegance here is that because both the continuous stream and the discrete tokens come from that same shared encoder, they naturally exist in a common semantic space. They share the same underlying visual information.
Ah, I see.
And this homogeneity, that's the key. The paper argues it significantly reduces that task conflict the LLM usually faces. The model isn't trying to read two different languages anymore. It's reading two formats of the same language.
That immediately sounds more coherent. You're not just patching systems together. You've got a unified source for the visual data. Okay, let's look at the whole pipeline then. We have the hybrid vision tokenizer at the input. What are the other main parts?
The overall architecture is actually quite clean. The second piece is the unified LLM decoder. This is the autoregressive part, the brain. It's built to take in any mix of text and those continuous image embeddings we just talked about. Its job is pretty straightforward. Predict the next token. That token could be a discrete image token or a text token, all from one shared vocabulary.
Like joint vocabulary, okay? And the third component handles actually creating the final image.
Correct. That's the image decoder. They've actually named it Ale Manzano, which is kind of fun. It's an auxiliary diffusion decoder. Specifically, they use the DITR architecture. Its only job is to take that sequence of discrete image tokens coming from the LLM and translate them into the final high-fidelity pixels of the output image. What's really noticeable is how simple the objectives are kept. The LLM just uses a single autoregressive objective, whether it's doing text-only tasks, I2T, or T2I. There aren't extra specialized losses or different task heads cluttering things up. And the whole design is quite modular. The LLM handles the semantics, the meaning. The image decoder handles the pixel details. This separation means they can scale these parts independently, which is a big plus for research and development.
Right, that makes sense. So this decoupled unified system probably needs a very specific training process to make sure those skills develop properly without interfering with each other. Can you walk us through the three-stage training blueprint they used?
Yeah, the training is progressive. It starts broad and then gets more focused. Stage 1 is pre-training. This involves massive scale. They feed the model a huge corpus with text-only data, interleaved image-text documents, I2T pairs, and T2I pairs. The goal here is just to teach the LLM general coherence across all these different modes. Then, stage 2 is continued pre-training. Here, they shift gears a bit. They use smaller amounts of higher quality data that's specifically chosen to build certain capabilities. This is where they inject things like documentation, charts, and data designed to improve fine-grained reasoning, sharpening its skills, basically.
Okay, scale first, then quality and specific skills. And the final step.
That's stage 3, supervised fine-tuning, or SFT.
Mm.
For this, they use carefully curated instruction data-specific examples of text instructions, I2T tasks, and T2I tasks. This stage is all about making sure the model reliably follows instructions when a user gives it a prompt, whether for generating something or answering questions about an image.
All right, let's get to the validation then. The proof is really the performance, isn't it? They first had to show that their main architectural choice, that hybrid tokenizer, was actually better than other ways of doing it. What did the ablation studies reveal?
The ablations were definitely key. They needed to prove the hybrid approach really does reduce that task conflict. So they compared it against a baseline that used only discrete tokens, running on a 1 billion parameter unified LLM. And well, perhaps unsurprisingly, the pure discrete method, which forces everything into those block-like tokens, showed a big drop in understanding performance, especially on benchmarks needing detailed perception, like reading documents. And what's more, they also compared it to the more traditional dual encoder approach, the one that struggles with different token types. Even that baseline didn't perform as well as Manzano's hybrid architecture on any of the understanding tasks they tested. So the data really backs up their hypothesis. The issue wasn't just how you encode the visual data, but whether the resulting tokens, continuous or discrete, share that common semantic foundation for the LLM.
So it sounds like they pinpointed the core issue, and their solution directly addressed it. When they tested the full unified Manzano model, how did it compare against models that are specialized, models that only do understanding or only do generation?
That was the encouraging part. The task conflict seemed minimal. That's the big takeaway. Even when they tested a smaller 300 million parameter version, the unified Manzano model performed pretty much on par with single task specialist models, which is strong evidence that this unification doesn't necessarily force you to sacrifice understanding accuracy just to get creative generation capabilities.
Okay, that's a significant finding. What about scaling? Did the benefits hold up as they made the models bigger?
They did. They saw what they call monotonic gains, basically. Performance just kept getting better consistently. This was true across all the understanding and generation metrics they tracked, including things like how well it followed prompts, GenAval, and used world knowledge-wise. This held as they scaled the main LLM decoder from 300 million up to 30 billion parameters. And they also found that scaling the separate image decoder, El Manzano, up to about 3.5 billion parameters gave substantial improvements in the quality of the generated images. Specifically, human evaluators noted better structural integrity.
Interesting. So let's highlight some of those benchmark results. Where did the Manzano 30B model really stand out, maybe even against proprietary systems or those specialist models?
The advantage was clearest in tasks requiring text-rich understanding. Manzano 30B actually got the top performance among all the models they listed, including the specialists and proprietary ones, on 4 out of 5 key text-rich benchmarks. These were ChartQA, TextVQA, DocVQA, and OCR bench. So that really validates the effectiveness of that continuous embedding stream for detailed perception. And it wasn't just perception. The model also ranked first in certain knowledge and reasoning areas. It came out on top on Science QA, MMMU, and MathVista, at least among the specialist and unified models listed in their comparison tables. And on the generation side, it achieves state-of-the-art results among unified MLLMs for both accurately following complex prompts and for generating images that reflect broader world knowledge.
Okay, so strong performance across the board in understanding and generation. The research also mentioned it can handle complex image editing. How does the architecture enable that capability?
Yeah, that comes back to that clean decoupled design we talked about. What they do is condition both the LLM and the diffusion decoder, El Manzano, on a reference image at the same time. The LLM uses its unified understanding to grasp the editing instruction and maintain semantic coherence. Meanwhile, the diffusion decoder uses that same image conditioning to maintain pixel-level control and consistency during the edit. And this joint conditioning allows it to handle a pretty wide range of editing tasks, things like instruction-guided edits, style transfer, but also in-painting, out-painting, even depth estimation. It shows it can combine that high-level semantic understanding with really fine-grained visual control.
So, looking at the bigger picture here, the research seemed to demonstrate that by focusing on a simpler unified input, that hybrid tokenizer, making sure continuous and discrete tokens live in the same semantic space, you don't necessarily have to make that trade-off. Unification doesn't automatically mean sacrificing understanding accuracy for creative generation. It addresses the conflict right at the data representation level.
That sums it up well. The main findings suggest that if you use clean, standard, autoregressive objectives, and critically, if you feed the LLM this improved, semantically consistent visual information, then a relatively straightforward and scalable architecture can achieve high performance in both understanding and generation simultaneously.
We've seen how unifying these two core tasks was successful here, and how that naturally led to robust image editing. So considering that success, the provocative thought to leave you with is this. How might this specific recipe, the hybrid tokenizer, the unified autoregressive backbone, the auxiliary image decoder, influence future work? Could it unlock progress in modalities beyond simple image generation, maybe towards things like deeply conversational editing or even broader reasoning capabilities that span modalities? That design pattern is definitely one to keep an eye on.